if you have got any specific doubts or any particular thing which you would like me to start discussing. So, Bonusri, can you tell me how many persons are online, by the way?
5%.
5 persons are online. I see. So, any particular specific thing which you have to tell me, or you would like to ask, or you would like me to get clarified? Any particular thing?
Mm, I'm only
5 persons are
through
online.
here.
So,
Yes, please.
any particular specific? Yeah, Bonusri, you wanted to say something? You would like
No,
me
ma'am.
to get clarified? Okay, fine. Then, see, what I have planned for today is that I would just like to scan through whatever we have studied. Maybe I'll start in a different way with a particular emphasis on why this particular subject has been taught to you, or rather, why phase equilibrium thermodynamics is very important for a chemical engineer. Now, assuming that all of you are chemical engineers, so in that particular, assuming that, so while we go through the recap, let us just see what a chemical engineer, or more specifically a process engineer. Process engineer means he or she can be in any particular stream, but is involved with development of processes, or running of processes, or maybe designing of processes. Now, whenever we have a process engineer, what are the different processes that they have to encounter, or they have to come across? They can be transport processes accompanied by chemical reactions, or not accompanied by chemical reactions. Okay. Even for reacting systems, they can be accompanied by different transport processes, which comprise of heat transfer, mass transfer, and momentum
Sorry
transfer.
for interruption, ma'am.
Yes, please.
There is a question that what is equilibrium in general?
Very good, very good. So as I go along, first I'll tell you why is equilibrium important. Then I'll come to the question of what is equilibrium. That is the question, isn't it? In general,
Yeah, yes.
Bonusri, see, the entire phase equilibrium is about what is equilibrium. I'll try to emphasize. In case you're not satisfied at the end, you'll ask me little more specific questions. I'll try to clarify it. Right. Now, just as process engineers, as I was telling you, see, we come across transport processes, we come across reacting systems. What are the different transport processes that we come across? That can be distillation, it can be absorption, adsorption, extraction, etc. What do these processes do? They are primarily separation processes. Okay, they are primarily used for either enriching any particular, suppose we have a benzene toluene mixture, out of which you would like to enrich the mixture to say 98% toluene or 98% benzene. So therefore, we use these transport processes for enrichment. We would like to, suppose we have a toluene acetic acid mixture, we would like to separate acetic acid from toluene. So separation can be one. We would like some particular reaction to occur so that we can get some particular desired product. Desired product can be anything. It can be a polymer, it can be a pharmaceutical, in pharmaceutical industries it can be a drug, in food industries it can be a food item, it can be in petroleum industries, it can be some particular product of cracking, etc., etc. So therefore, primarily process engineers, that's a better word for chemical engineers, primarily process engineers, they are concerned with different type of processes involving chemical reactions, not involving chemical reactions. The primary purposes are either enrichment, separation, or reaction. Now, whenever you have to undergo, or rather execute these processes, what do you want to do? Whether be it separation, enrichment, reaction, whatever it is, you first have to mix the two phases, right? Whenever you mix the two phases and to try to have an intimate contact between the two phases such that the mass transfer is maximum. After the required mass transfer is over, then you separate the two phases so that with those separated phases, you can go on for downstream processing. Now, when you are mixing the two phases and you would like to have the maximum amount of mass transfer, you would like to know what is this maximum amount of mass transfer. For any particular two phases, what is the maximum amount of transport that you can get? This is dictated by phase equilibrium. When the two phases are equilibrium, the composition of the two phases are the maximum that you can get under that particular condition of temperature, pressure, and other operating parameters. So therefore, how well you are performing a process, that depends on how close you have approached to the equilibrium process, right? So therefore, if you're closer to the equilibrium process, then you can you are performing much more better. So therefore, whenever you are designing any particular system, it may not be a separation system, it's just a process system. Suppose you have got a available feed stream. Now usually when you have got a feed stream, what are the known parameters? For a batch system, usually the composition is known, the quantity of the batch is known. For a continuous stream, the flow rate is known and the inlet composition is known. Now, based on this, you are supposed to perform a separation or an enrichment. Now, what is the separation or the enrichment, that what is the maximum that you can get? The see, this will be primarily specified by the client, right? The client will set the purity limits in terms of the concentration of the specific components, right? Suppose the client says, from a benzene toluene mixture, I want 98% pure benzene. So therefore, he is going to give you some inputs. The inputs which he gives you are usually, suppose it's a flow system, then the inputs will be flow rate and inlet composition, or maybe for a batch system it will be composition and the quantity. And he will have certain particular design targets which you are supposed to meet for designing that system. What will be the design targets? Based on this particular composition, he would specify the purity limits, that this amount of purity or this amount of separation I want. Then remember one thing, whatever I have shown you, out of these particular processes, it's only distillation where we do not add an external phase. Instead of that, what we do, we add heat. Whenever we add heat, then suppose we have a liquid mixture, it some amount of the liquid, it vaporizes, and then there is mass transfer between the vapor and liquid, as a result of which enrichment occurs. For all other processes, if we have any particular solution or we have any particular mixture, we add a third component to it, and then this particular third component, it creates a separate phase. In distillation, the separate phase was created by heat. For all other processes, the separate phase has to be added from outside. For example, in absorption, we have a gaseous mixture, we add a liquid outside. For the case of stripping, we have got a liquid mixture, we add a gas phase from outside. If it is adsorption, we have either a liquid mixture or a gaseous mixture, we add a solid for adsorbing the desired component. If it is extraction, we have a liquid solution, we add another liquid to it, such that the the liquid which we have added, that extracts the desirable component from the solution that we have. So therefore, what do we have? Every time we find that we actually have two phases. Now therefore, from the phase where the desired component has been recovered, from there also the desired component has to be recovered back. So therefore, the performance targets will first be the purity that you need, the recovery percentage of the desired component from the feed, and then maybe there will be some particular specific property limits that they will be specifying for the separated streams. These particular specific property values, they will depend upon, suppose they want to discard any particular stream, so therefore there will be some guidelines on the composition, or some guidelines say on the specification of the separate streams which can be discarded. This particular streams, they can be used in a reactor, so therefore there will be some particular specific properties depending upon the downstream processing that is going to happen with these particular streams. Along with that, there will be some particular additional constraints as
Sorry
well.
to interrupt, ma'am.
Yes, please.
A question for Mohan, that he wants to know a comparison between the thermodynamic equilibrium, static equilibrium, and dynamic equilibrium. And also, he is asking that I had understood. Yes,
Yeah,
yes.
please. Also, is asking that.
I had understood the equilibrium that no change in state of system. Am I correct? He is asking.
Okay, then I think Mohan, just tell me one thing. Should I skip these things and directly go to your question? M- Uh, can they respond, Bonusri? Or
Yes,
is it
yes, in chat.
in chat? So just
Mm.
ask him whether I should skip these things and I should go directly to his question, or I should proceed in this manner and I'll be coming to his question shortly.
Okay, okay.
Okay, he can very well respond. So therefore, then what I do is, say, I just wanted to emphasize the importance, right? So Mohan, should I go ahead, or do I go directly to your question? Well, I think I'll go directly to his question. Bonusri, can you just specify the question once more, so that I can go directly to his question? So just I'll just summarize a little. So therefore, we find that whatever things we are required to know, for example, the phase. I'll just go here. Yeah. So whatever things we are required to know, the purity limits and etc. etc. All those things, they depend upon the phase equilibrium, right? Because remember one thing, whenever we have two phases, be it vapor liquid phases, be it liquid liquid phases, be it gas liquid phases, for all these cases we have interface mass transfer. And interface mass transfer between two immiscible phases, they take place in a direction such that equilibrium is attained. Because remember one thing, finally, always we have spontaneous processes are directed towards attaining of equilibrium. And if we want to perform any non spontaneous process, if we want to move away from equilibrium, if we want to move away from equilibrium, then in that case you will find out that we have to supply energy from outside, so that we can make that process happen. But whenever we find that there is any particular spontaneous process which is occurring in nature, that the purpose of the process is to 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 ensure that the final state that we get, that is the equilibrium state, or that is the state that we would like, right? So therefore, if we want to find out what is the best possible transfer that can take place, so therefore the best possible transfer can take place is the transfer which takes the system to an equilibrium state. So, therefore, phase equilibrium data pertaining to a transferable component in any particular transfer process, it represents the limiting composition for the phases in each ideal state, right? And therefore, whatever separation that we can attain in any mass transfer process, that depends upon how much departed it is from the equilibrium composition. Well, now I would like to explain what is equilibrium. Bonusri, can you just repeat the question which was asked?
Sure, ma'am. He wants to clarification between the comparison of thermodynamic equilibrium and dynamic equilibrium.
I
And
see.
he also
Huh.
asking that he had understood the equilibrium that no change in state of the system. Is
Well,
it correct? The concept is
fine.
correct, he is asking.
Okay. The first question is that you had understood equilibrium to be no change of state. I'll just correct you. It is not no change of state. It is simply no tendency to change the state. See, there's a difference between these two, right? For example, suppose there is one particular system, say a liquid is there. Okay. On that liquid you are exerting a very high pressure, but there is no change in volume of the liquid just because it is incompressible, but there is a very high pressure on the liquid. Under this condition, the liquid is not under equilibrium because there is an unbalanced pressure on it. Because of the pressure, maybe none of the properties are exhibiting any discernible change, but that does not mean that the liquid is in equilibrium. Equilibrium does not mean that the properties do not change. The equilibrium means that there is no tendency of the properties to change, which implies that a system in equilibrium is not subject to any unbalanced forces. And these unbalanced forces, they can be in terms of pressure, which implies that it is under mechanical equilibrium. The temperature at all points within the system and between the system and the surroundings, everything should be at the same temperature, which implies that the system is under thermal equilibrium. The chemical potential or the fugacity of each component of the system, sh- rather in the different phases of each component of the system, they should be equal, which implies that the system is under chemical equilibrium. Mostly when we are talking about equilibrium in the as chemical engineers, we refer to chemical equilibrium, but please remember that when we define thermodynamic equilibrium, it is very important for you to remember that thermodynamic equilibrium can be defined. This is something very important that you should be remembering, that whenever we are talking about thermodynamic equilibrium, it is the simultaneous satisfying of mechanical equilibrium, thermal equilibrium, and chemical equilibrium. When all these are simultaneously satisfied, only under that we say that the system is under thermodynamic equilibrium. What does mechanical equilibrium means? That there is no unbalanced force acting on the system, or in other words, P of, say, phase alpha will be equal to P of the phase beta, and so on. So therefore there is no pressure difference between any two points of the system, and also between the system and the surroundings. Thermal equilibrium, what does it mean? That the temperature among the different phases and also the temperature of the surroundings, everything is equal, such that there is no thermal driving force, or there is no heat flow between the system and the surroundings, or between different components or different parts of the system. Chemical equilibrium, normally it is defined by chemical potential, but as we had already discussed, that chemical potential is an abstract quantity. So it's better that we had substituted chemical potential with fugacity, and we had defined chemical equilibrium in terms of fugacity. So if you try to find out the starting of chemical equilibrium, we find that the basic starting had come from the second law of thermodynamics. From second law of thermodynamics, or rather from the first and the second law of thermodynamics, what did we get? I'll just insert a slide, and I would like to write here. From the first law, what did we get? We found out the first law is TD, sorry, very sorry. First law was du equals to dq minus dw. Remember, all these things were based upon the sign convention, that q entering is positive, w being done is positive. Based on this, we had developed the, or rather we had expressed the first law of thermodynamics. Then from the second law, what did we get? From the second law, we we got, this was the second law, that dq, sorry, dq is less than equal to, let me make all q's capital, less than equals to tds. Based on these two equations, what can we write down? We can write down du equals to tds minus dw. When we have only PV work and nothing, for only PV work, under that particular condition, what do we have? We have dw equals to pdv. Accordingly, from this equation, we get du equals to tds minus pdv, right? Just one thing I would like to say, that all these are capital. You must be, by this time, you must have understood that capital refers to total properties and small refers to the molar properties. So from this particular equation, what do we get? That under equilibrium conditions, we can either write it as du at constant capital S capital V equals to 0, or we can arrange this and we can write it down as ds at constant u constant v equals to 0, which signifies equilibrium. Now if you look at this particular equation, when the energy of the system is constant and the volume of the system is constant, under this particular case it means that the system is an isolated system. So for an isolated system, equilibrium, for the chemical equilibrium in particular, that is defined as ds equal to 0. But as I had already mentioned in the class, that mostly it's very, we don't deal with isolated systems, and also it is very difficult also to maintain an isolated systems. So therefore, based on the interaction between the system and the surroundings, we had defined different types of equilibrium from this particular basic equation, sorry, from this particular basic equation, right? And if you recall the criteria of equilibrium which we had defined, which can be defined for any particular system
Ma'am,
interacting, yes please.
Mohan is again asking that as
Huh.
I learned that to specify the state of thermodynamic properties, it should uniform throughout the system and it should not change with time. What if properties do not satisfy this? Uh, then what will be the condition? He's asking. And another question that
Just 1 minute. Before Bonusri, before you go, I'll just clarify one more question that he had asked. First question was, what is equilibrium? I believe I've already clarified that thermodynamic equilibrium is the simultaneous satisfaction of mechanical, thermal, chemical equilibrium. Second question was dynamic, static, and your thermodynamic equilibrium. Now, let me tell you one thing. Whenever we are dealing with thermodynamic equilibrium, it is a dynamic equilibrium. Why do we tell that it's a dynamic equilibrium? Because when when system is in equilibrium, it's not that there is no transfer among the systems. Definitely there is transfer among the systems, but the rate of forward transfer is equal to the rate of backward transfer. For example, suppose I write down a very simple equation, say the standard thing which you have learned in schools. Well, this is the equation, okay? Nitrogen, hydrogen, in presence of the catalyst iron and molybdenum, they form ammonia. Under equilibrium conditions, you will find that the composition of nitrogen, hydrogen and ammonia, it is not changing. Please do not think that means the reaction has stopped. It simply means that this is a reversible reaction. Under equilibrium, the rate of forward reaction is equal to the rate of backward reaction. So therefore, it's always dynamic equilibrium that we talk about. We do not talk about static equilibrium in thermodynamics. There is also one other thing which I would like to mention. See, if you remember in your school, there was a very standard thing, a neutral equilibrium, stable equilibrium, and unstable equilibrium. If you remember, so therefore this was a stable and this was a neutral, this was an unstable equilibrium. If you remember that, if you just revert it from its original position, the equilibrium is disturbed. Here if you revert it, it comes back. In this particular case, nothing happens. For the case of thermodynamics, we always deal with stable equilibrium. For all the cases that we deal, we deal with stable equilibrium. There are certain unstable equilibrium cases as well. What are the unstable equilibrium cases? For example, say subcooled liquid, superheated liquid, that means water above 100 degrees centigrade. There can be cases where we can take water or it can be made to remain liquid slightly above 100 degrees centigrade, but that's an unstable equilibrium. By just changing any particular condition a little, it comes back. It either changes to the vapor or it cools down to the liquid. Subcooled vapor, say steam below 100 degrees centigrade, 1 atmosphere's pressure. All these cases are your unstable equilibrium. But normally, when we talk in thermodynamics, we talk about stable equilibrium, we talk about dynamic equilibrium. There is nothing stable in thermodynamics because we're always dealing with systems between which mass transfer is occurring, and we would like to find out that what is the maximum amount of mass transfer that will go on. The maximum amount of mass transfer that can happen in any particular system is when, for example, suppose I take up some particular system, say I take up some particular, say simply I take up one particular this is one system and this is another system, right? And so therefore between these, mass transfer or occurs in both directions. At some point of time, when you measure the composition of this and to measure the composition of this, you find that the composition does not change at any particular position here. It does not change with time. So that means when this happens both for this and both for this, for the two phases, then we say that the system is under thermodynamic equilibrium, provided the temperature, the pressure, as well as the chemical potential of each component in both the phases are the same, right? So but do not think that under that condition the any sort of transfer between phase A and phase B has stopped. No, transfer goes on be from phase A to phase B, but at equilibrium, the transfer from A to B is the same as the transfer from B to A. Yes, Bonusri, what is the next question? Bonusri?
Yes, ma'am.
Yeah, what was the next question that he asked?
How many independent intensive properties are required to fix the state of pure substance?
Very
Is it
correct.
one or two? And give some justification.
See, there is first thing is there's an equation which justifies everything. How many? See, first thing is how many intensive properties are required to specify the state of a pure substance? That is the question, isn't it?
Yes, ma'am.
The first thing I'll tell you, it depends upon in what state the system is. If a pure system is in one particular phase, say a liquid phase, then in that case, what is F equals to C minus P plus 2, right? So you have got one particular component in one particular phase. So therefore, F is equal to 2. So therefore, when you have got up, say, water, so if you want to specify the state of the system, you need at least two particular parameters. What are the two parameters? Temperature and pressure, right? Same water if it is in equilibrium with vapor. Then in that case, what do you get? Your P, this is equal to 2, and in that case C is definitely 1. So therefore in this particular case, what do you have? You have 1 minus 2 plus 2, which is equals to 1. So therefore for two states in equilibrium of a pure substance, either temperature or pressure can be specified, the other automatically gets specified. But if it is in a pure substance in a single state, then in that case both temperature and pressure can be varied independently. So therefore fixing one does not fix the other. You have to specify both of them. Suppose now I take a salt solution. In this same water, I add some amount of salt. What happens in this case? If I add some amount of salt, then in that case C becomes equal to 2. So therefore, in this salt solution, then what do we have? For the salt solution, we have F is equals to 2. Liquid state is there. Sorry. minus 1 plus 2. Just give me 1 minute. Yeah. So what do we get then in this particular case for the solved solution? It's 2 plus 2, 4 minus 1 equals to 3. So what does it mean? When we have a solved solution, just specifying temperature and pressure is not enough to completely specify the state of the system. We also need to specify the composition of the solution. Now, the same solved solution is in equilibrium with the vapor. When it is in equilibrium with vapor, then what happens? That under conditions when it is in equilibrium with vapor, P becomes equals to 2. So therefore, in this particular case, what will you have? You have got two components, salt and water, and then they are in two phases, liquid phase and vapor phase. So therefore, again in this particular case, you have there are two variables only. So therefore, either you specify temperature and pressure, then in that case, under this particular temperature pressure, the composition in the liquid phase and the vapor phase gets fixed, or else you specify the composition of the salt solution in the liquid phase, and under that particular condition, your moment the composition in the liquid phase and the temperature, if these two are specified, then the condition, or rather the pressure, it automatically gets fixed. Because whenever we are having a salt solution in equilibrium with its vapor, then all the what are the properties? The composition of the salt solution, the temperature, the pressure, all of these cannot be varied independently. I assume that in the vapor phase we don't have salt, quite naturally, because it is a non-volatile thing. So therefore, the variables that you have, they are temperature, pressure, and the composition of the salt. When the salt solution is just in the liquid state, you can vary all the three independently. When the salt solution is in equilibrium with it, with the vapor of this particular solution, under that particular case, either you vary temperature, pressure, or you vary temperature, composition of the solution, or you vary pressure and composition of the solution. You cannot vary all the three together, right? Again, there's something very interesting which I forgot to tell you. We were talking about, again I come back to the pure system. I told you that when we have a completely a pure system in a single phase, under that case we found out that for that particular case, the total number of variables was 2, right? So therefore, temperature and pressure can be specified. This same pure component, when it is in equilibrium with its with, say, the liquid is in equilibrium with vapor, or the solid is in equilibrium with vapor, whatever it is, then under that case we found that either temperature or pressure can be varied. Suppose we are talking about a pure substance in its triple point. What is a triple point? When the vapor, liquid, and the solid, all of them can coexist. For a triple point, what are the number of phases that we have? For the triple point, the number of phases that we have, this is equals to P will be equal to 3. Under that particular condition, if and C is 1, so therefore what do we have? F, this is equal to 1 minus 3 plus 2, which is equal to 0. Which means that at the triple point, none of the properties can be varied independently. The triple point is a fixed point which cannot be varied. It is a property of the pure substance. So therefore, when you tell what is the number of and remember, this is the number of minimum intensive properties that can be varied to completely specify the state of the system, you have to specify what is the state that you want to specify. Is it in one phase, is it in two phase, or is it at the triple point of the two substances? In the same way, I can tell you that suppose I have, say, a, a benzene toluene mixture, right? So therefore, there is a benzene toluene mixture. Again, in this particular case, what can we have? We can have, this is the thing, right? So there are two components, benzene toluene liquid solution we have. So for this, just like the similar to the salt solution, for what will you have? You are going to have, this is 2 minus 1 plus 2. So therefore 2 plus 2, 4 minus 1, this is equals to 3, similar to the salt solution case itself. So when this benzene toluene solution is liquid, what are the things that we can vary? We can vary the temperature, we can vary the pressure, and we can vary the composition of either benzene or toluene. We cannot vary all the four independently. And that's quite natural, because finally xb plus xb has to be equal to 1. Right. But if this same benzene toluene liquid mixture that is in equilibrium with the vapor mixture, in this particular case, unlike the salt solution, benzene and toluene can exist both in the liquid state as well as in a vapor state, where these two states are in equilibrium with one another. Right. For this case also, similar to the salt solution case, we can write that there are two components, there are two phases, and therefore in this particular case the total number of variables become 2. That means, what are the total number of properties when liquid solution of benzene toluene is in equilibrium with vapor? The total number of properties are temperature of the system. It's an equilibrium system. So therefore, one particular temperature defines the complete thermal state of the system, pressure of the system, the composition of benzene in the liquid phase, the composition of benzene in the vapor phase. Out of all these four particular variables, we can vary two. It can be any two. The other two automatically gets fixed up. Right. So therefore, depending upon what you have, there's something, another very interesting thing I'll tell you. Again, if I go back to the salt solution, in the salt solution, what did I tell you? We have salt and water. Right. So therefore, just as I had told you for the salt solution in this particular case, okay, I'll go to this case, I'll write once more. So therefore, we are having salt plus water. Agreed. Now for this case, we are having C equals to 2. It's a salt solution. P equals to 1. What is F equals to? It is 2 minus, sorry, very sorry. It is 2 minus 1 plus 2. Right? So therefore, this is equal to 3. So for a salt solution, we can vary temperature, we can vary pressure, and we can vary the concentration of salt. Fine. Now, suppose we keep on adding salt such that the solution has become saturated or supersaturated and some amount of salt has come out from it. Right. For such a case, actually, we have two phases. Right. So when the solution becomes supersaturated, for that particular case, the F is C minus, sorry, 2 minus 2 plus 2. So therefore, in this particular case, the number of intensive properties are 2. Why? Because only temperature and pressure can be varied if you want to keep the solution under that particular supersaturated state. For the supersaturated state, temperature, pressure, and composition, all three cannot be varied. Now suppose the supersaturated salt solution is in equilibrium with its vapor. Then in that case, what do you find? We find that the total number of phases that we have for a supersaturated solution, P becomes equal to 3, because there is a solid salt, there's a liquid solution, and there is a vapor in contact with the liquid solution. For that particular case, what do you expect? You will have, there are two components. So we have two. There are three phases. We have this. So therefore, for such a situation, only one component can be varied. Right. So when you have a supersaturated salt solution in equilibrium with its vapor, under that particular condition, either the temperature or the pressure or the composition can be varied. Maintaining a supersaturated solution where some amount of solid has already crystallized out as a solid phase. When this particular state is in equilibrium with its vapor, then under that condition only one property can be varied. So is this part clear to you?
Another question, ma'am.
Yes, please.
Ma- he's asking that, ma'am, you said that number of independent intensive properties of two-phase pure substance is 1. We need either saturated temperature or saturated pressure along with dryness fraction to get all properties. Is dryness fraction property is a property of a system?
Definitely dryness fraction or the quality is a property of the system. But when you are talking, see, there are two things that you have confused. One is whenever you are talking about a dryness fraction, that means there is a sorry, it's a liquid and a vapor in equilibrium, right? So therefore the dryness fraction, it is just the proportion of the liquid or the proportion of vapor. Fine. So therefore that is definitely something very important, but whenever you are talking about dryness fraction, it automatically implies that there's a liquid and a vapor in equilibrium. And then the situation, it happens just like I have told you. Whether I have written it here, I don't remember that. Yeah, so for that particular case, when you're talking about a dryness fraction, that means you have got steam, and what is the amount of water there, the quality of the mixture. Basically, suppose you have steam and you want to know the quality of the mixture. So fine, for that particular case, as I've told you, the component is one. For that particular case, the phases are two, right? So for that particular case, i- if you are having one component and two phases, then naturally for that particular case your system gets fixed by one particular component. If you're, for example, I'll just draw it and show you. Let me go for one more slide. For this particular pure substance, suppose it is water only, right? So therefore this is the liquid plus vapor dome. This is the liquid and this is the vapor, and we are drawing the, say, the pxy diagram or the txy diagram, whatever it is. We can also draw the pxy. So therefore, oh, so this is the vapor dome. It's not very well drawn. Wait, let me draw it better. Yeah. So therefore, this is the case. This is the critical point. This is the triple point, and this here liquid is there. And in this particular case, below this we are having solid plus vapor, and this is the triple point curve. In this case, when you are talking about the and let me draw it. This is one particular isotherm that we are drawing, right? Or else if you make it txy, then in that case also the graph will be slightly different. Now when you are there inside this particular dome, liquid vapor dome, then if you specify the pressure, then in that case the pressure gets specified, and within this dome we know that it's an isobaric isothermal. Both the pressure and the temperature are maintained constant, right? And these are the quality lines that you have. Fine. So therefore, if you specify one, when you are specifying temperature, then in that case, since everything is under saturated conditions, so at that particular temperature, there'll be one particular saturated pressure. Moment that saturated pressure temperature they are fixed, it falls on a particular quality line, and therefore the quality also gets fixed. So within this particular liquid vapor dome, there is only one property that you can vary. Moment that one property gets fixed, all other properties get fixed. Yes, what are the properties inside this dome? Inside this dome, the properties which are the temperature of the system, the pressure of the system, the quality of the system. And I'll tell you one more thing here. I do not remember whether it was mentioned. Just for that particular reason, since in within this particular system, you can vary. If you know the temperature, you know the pressure, but you do not know the quality, right? For one particular temperature pressure, the system it can lie here it can lie here, it can lie here, it can lie on the saturated curve as well. You do not know exactly the quality. And again, from Gibbs phase rule, there is no way by which you can find out the quality, because Gibbs phase rule, it does not specify it does not depend upon the total amount of the system. It does not depend upon the composition of the system. It is just dependent on the number of phases, number of components. Irrespective of how much of each component is there, it will just tell you that what are the minimum number of properties that are needed to specify the state of the system. Moment those number of properties are specified, the state of the system gets fixed. It But it does not tell you that whether, say for example, water and water vapor mixture, right? For this particular system, if we have 99% water and 1% vapor, then also the and if we have 99% vapor and 1% water, for both these things, f will be predicted as 1. Okay, so therefore it does not, the quality, it's very difficult to find out the quality from the temperature pressure conditions. So that's why, if you remember, in order to find out the quality, what we need to do, we need to take this particular state by some means into the single phase region. Moment we can take it to the single phase region, under that condition we can specify both the temperature and the pressure, and then based on that, the quality of the system in the initial state can be specified. How can we do that? If you remember that we had mentioned this, one thing that we can do is, suppose under this particular condition, what is the molar volume? The molar volume of the mixture, this is x v, say vapor, gas or vapor, whatever it is, 1 minus x vl. What is the molar enthalpy of the system? xag plus 1 minus x hl. So therefore, unless we can know x, we cannot find out hm. Now, when the system is within this particular state, it's not possible for us to know the enthalpy of the system, right? Because that depends on x. So if we do not know x, we cannot find out the enthalpy. What we do, we maintain an isenthalpic condition and bring it to the single phase system. Moment we can bring it to the single phase system, we can measure its temperature pressure in the single phase system. From measurement of temperature pressure, we can fix the enthalpy of the system. Moment the enthalpy here is fixed, we have followed an isenthalpic path to go from the single phase to the, sorry, two phase to the single phase system. So therefore we know that the enthalpy here is equal to the enthalpy, say at this particular state we have moved along an isenthalpic line. So this state 2, since it is in a single phase state, so therefore in this particular state H2, this is a function of temperature pressure. We can measure them independently and fix up H2. Now we know that this H2 is equals to H1. Once we know H1, then from this H1 we can say that this H1, it can be expressed as in terms of the saturated enthalpies of the vapor and the liquid. Saturated enthalpies can very well be found out. So from there we can find out X. This is one particular way of measuring the quality of any particularly of steam water mixtures. This is one particular way of finding out the dryness fraction or the wetness fraction of the of steam for, in any particular equipment or in any particular system. I understand this is more or less clear to all of you.
Then he is asking that, then
Huh.
why don't we tell that we need two properties which are either saturated pressure along with dryness fraction and saturated temperature along with dryness fraction?
I did not get the question. Can you just repeat it once more?
He is asking that, then
Hmm.
why don't we tell that we need two properties which
No,
are
no.
either.
Listen, one thing. There's no question of telling. See, the thing is, Gibbs phase rule, it has been derived. The derivation, it's quite elaborate. It has been derived to tell you what are the minimum number of properties that are required to specify the state of the system. This is what it tells you. From Gibbs phrase rule, we know that F is equals to C minus P plus 2. This is what we know from Gibbs phase rule. There's no question of telling, right? So when a system is in thermodynamic equilibrium, then the minimum number of properties that are required to specify the state of the system, that is given by Gibbs phase rule. Once those minimum number of properties are specified, the state of the system is specified, irrespective of the composition of the system. Right. So therefore, moment when we have a liquid and a vapor in equilibrium, that means we have moved from the single phase zone to the two phase zone. Now, moment we have moved into the two phase zone, then under this condition, we know both the temperature and if we fix the temperature, pressure gets fixed. If we fix the pressure, the temperature gets fixed, because inside the two phase dome we have a isobaric isothermal curves. All these curves here, they are isobaric isothermal curves, right? So therefore, within this particular system, we know that if we specify in order to specify the state of this system, we have only one property to play with. That can be temperature, that can be pressure. We can play with either of them, right? Moment we play with either of them, the state of the system gets fixed, whether it is this or whether it is this line or this line, it gets fixed. But in this line where it is going to lie, that is not fixed. So in order, if you want to evaluate that where it is there, then the quality can be found out by this particular process. But what are the minimum number of properties that you need to fix the state of the system, or that you need to evaluate the state of the system? That is given by the Gibbs phase rule under all conditions. So therefore, there is nothing that we are telling. It is just that it is specified by Gibbs phase rule, which has been obtained from a very quite an elaborate derivation, which I do not remember. I think I have done it in the class. I don't remember, but this has come from this elaborate derivation. Now here I would like to tell you there are two limitations of the Gibbs phase rule. Gibbs phase rule holds irrespective of the proportion of the two of the or rather irrespective of the composition of the system. It holds irrespective of the size of the system. So therefore, if we have water in a bucket, we have water in a test tube, we have water on the floor, wherever we have water, it always tells that when we only have water, then its state can be specified by its temperature and pressure, irrespective of the amount of water. When we have a wet steam, then under that case, it tells that the your for that particular wet steam, its state can be specified by measurement of one particular property of the system. If for that particular wet steam, either you can fix its temperature, or you can fix its pressure, or you can fix its quality. But moment you fix one particular point, the state of the system gets fixed. But in this particular state, if you want to know the composition, well, then it is difficult, because from one particular point it's difficult to get the composition. So therefore, in order to estimate the dryness fraction, you have to follow this particular technique. But the state of the system, moment it is within this particular dome, it gets fixed by specifying either the temperature or the pressure of the system.
Ma'am, one more question.
Yes, yes, definitely.
As I learned that to specify the state by thermodynamic properties, it should uniform throughout the system and it should not change with time. What if properties do not satisfy this? Then how do we apply all the thermodynamic laws?
Let me tell you, whatever has been taught to you, they are this is classical thermodynamics. They are meant only for systems which are in equilibrium. We have another field of thermodynamics, which is non-equilibrium thermodynamics or statistical thermodynamics, which has not been covered here. Whatever has been covered in this particular lecture, or this particular subject, or this particular course, that is just classical thermodynamics, where all the things that have been told are applicable for systems which are in thermodynamic equilibrium. Non equilibrium thermodynamics is an altogether different branch of thermodynamics, nothing to do with what we have learned so far. So, therefore, remember one thing, because whenever we are specifying properties, we are specifying properties for systems which are in equilibrium. If a system is not in equilibrium, then you cannot specify the properties of the system, because when a system is not in equilibrium, every single point of the system maybe it will have different temperature. So you cannot say that the suppose for any particular system, maybe the temperature at one point is 20, somewhere 22, somewhere 25, somewhere 30, somewhere 35. Can you specify the temperature of this system? So therefore, whenever we are talking about the state of the system, we mention it or we don't mention it, we are talking about the equilibrium state of the system. Whenever we talk about systems when states of a system in thermodynamics, we always refer to equilibrium states. This is something which you have to remember, because when a state is when a system is not in an equilibrium state, then the properties have got no meaning at all. Because what are properties? The properties are characteristics of any particular system which specify the system. When those particular characteristics they keep on changing, then what is the value that you will quote? Suppose I have got water at 25 degrees centigrade. You ask me what is the temperature of water, I say it's 25 degrees centigrade, right? If in that particular water, wherever I put the thermometer, somewhere I get 10, somewhere I get 15, somewhere I get 35, can I tell you the temperature of the water? So therefore, under that condition, I cannot specify the properties of the system. So therefore, whenever I am in a position to specify the properties of the system, definitely the system is in an equilibrium state, more specifically under thermodynamic equilibrium, which implies that it has got a constant temperature, a constant pressure, and a constant chemical potential, based on which the other properties of this system can be estimated. I hope I am clear enough. Bonusri, just see if there are any other questions from him.
No, ma'am.
And you can also request him that if he has some other questions, he can directly contact me. Because see, this typing, if he can ask me questions, possibly it's going to be better. So therefore, if he wishes, he can contact me by email or something, and then we can have a better discussion and I can explain things to him better. Because then that case he can counter my arguments and he can place his. Is the dryness fraction part clear to him? That we cannot specify the dryness fraction of wet steam, because under that condition, steam, it is whatever be the dryness fraction, it remains under the same temperature and pressure. Moment we have reached saturated conditions, from the saturated liquid to the saturated vapor, and a mixture, a two-phase mixture, for everything the temperature and pressure remains the same. So therefore, once we have water at 100 degrees centigrade, we start heating it. Suppose initially we had got pure water, then we had 90% water, then 80%, then 70%, and finally we had 10% water, and then we had 0% water. For this entire particular state, the water was at 100 degrees centigrade and 1 atmospheric pressure. So therefore, the state got fixed. Since the state got fixed, under this condition, if you have to find that the composition of water, that within this particular state, when the water had entered the two-phase mixture, under that particular condition, what is the composition of water? In order to find that, then what we need to do, by some particular isenthalpic process, either by expanding the steam or whatever, we have to move from, where is my pen? We have to move from We have to move from this particular state to the single phase region. Only then we can specify the enthalpy or any other property. Based on this particular property, since we have moved along an isenthalpic line, we know the original in the original state, this the property of this system. From that we can find out the quality, because whenever the quality is changing, the temperature and pressure remains the same. Now if you change the temperature or the pressure, we'll get another particular state of the system, right? So for this particular state of the system, whenever we are moving from saturated liquid to the saturated vapor phase, no matter how the composition is changing, Gibbs phase rule keeps on telling us that the state of the system is specified by its temperature or its pressure. You cannot independently vary these. And Gibbs phase rule, it is not dependent upon the size of the system and the composition of the system. So anything else, Bonusri?
No, ma'am.
So I understand equilibrium is quite clear to you. And see, whenever we are dealing with your in chemical engineering, whenever we are dealing with equilibrium, then for most of the cases we deal with for vapor liquid equilibrium or liquid liquid equilibrium, right? So therefore, depending upon what is the system or what is the process that we are dealing with, if it is a distillation, then we deal with vapor liquid equilibrium. If it is absorption, then we deal with solubility curves, okay? Because the solubility curves gives us what is the maximum amount of, say we have a carbon dioxide air mixture. From this, carbon dioxide has to be absorbed in, say, some amine solution. What is the maximum amount of carbon dioxide that can be absorbed? That will depend upon the solubility of carbon dioxide in the amine solution. So therefore, there the equilibrium curve is the solubility curve. Suppose we have a, say, ethanol water mixture. We want to separate it by distillation, right? In this particular case, the composition of ethanol water in the liquid state and the composition of ethanol water in the vapor phase, which is in equilibrium with this particular liquid state. So this decides what is the amount of separation that we can bring about. For example, if I can take you to the, there's no point in dealing with the estimation of properties. So finally, the condition of equilibrium which was reframed, if you take up, see, there were different conditions of equilibrium that we had specified, right? The conditions of equilibrium that were specified. So initially, if I tell you the condition of equilibrium that was specified as, there were different conditions. For an isolated systems, the condition was, this is the condition, right? For a system at constant temperature and pressure, this is the condition of equilibrium. From this particular condition of equilibrium, for other things we had, this was the condition of equilibrium for a system which was at constant entropy and pressure. And this was the condition of equilibrium for a system at constant temperature and volume, right? Now, usually we deal with systems at constant temperature and pressure. So therefore, this particular relationship is very important. Then what we did, for suppose there are two phases in equilibrium, say this is the vapor phase and this is the liquid phase, both of them are in equilibrium, right? So therefore, this whole system is closed system, but each one of them, they are open systems. So therefore, when we are dealing with open systems, then if you recall, we had found out dg was equal to minus sdt plus vdp plus mu dn. If you remember, if it is a pure substance, if it is a pure substance, and if it is not a pure substance, then we put I equals to 1 to n, when this particular I, it refers to the component number. There are n number of components here, right? And therefore, this also refers to each particular phase as well. So therefore, for that, suppose we are having multiple phase and multiple components, then in that case, what do? Then for each particular phase this holds, and so therefore if there are pi number of phase alpha equals to 1 to pi, then it implies that for each particular component I, its chemical potential in alpha phase, in beta phase, everything has to be equal. And it implies that for each particular phase the temperatures have to be equal, or in other words, dt has to be equal to 0, the pressure has to be equal, and the chemical potentials has to be equal. Now from, so therefore, from the equation dgtp equals to 0, we found out that under equilibrium conditions we get at constant temperature and pressure, this implies mu I dni equals to 0. Right, for each component I, this is the thing, when one component I exists in different phases, for each particular component in the different phases, this particular equation is applicable. So therefore, if anything is at equilibrium, how do we know that? We have to calculate mu. It is, mu is an abstract quantity. So therefore, I had already explained in the class, I think you will be remembering. So therefore it was very difficult to, it's very difficult to find out mu, right? So but we know what is mu equals to. Mu equals to del G del N at constant T and P. Or in other words, this is nothing but equals to the molar Gibbs free energy. Right. So therefore, if this is true, we know dg equals to minus s dt plus v dp. So we can also write down d mu equals to minus s dt plus v dp. Right. So therefore, from here, then we find that suppose we are dealing with at constant temperature, then we can write d mu equals to vdp at constant temperature. For an ideal gas, what do we get? For an ideal gas, vdp is nothing but equals to rt by pdp. So therefore we find for an ideal gas, we find that d mu 0, this is equal to rt d ln p. Or for an ideal gas, suppose we integrated, say, from state 1 to state 2, we integrated from state 1 to state 2. So we know mu 2 of the ideal gas. Ideal gases are denoted by this 0 minus mu 1. This is equals to RT ln P2 by P1. Right. We have this. So we find that for an ideal gas, we can relate the chemical potential with the physically realizable quantity, which is pressure. We liked this relationship. So then it was felt that if such a relationship can be applicable for any other
And
case, yes, please.
Mohan is still can't understand why
Yeah.
don't we add the dryness fraction with saturated pressure.
How do you, I see this? I think I have to interact with him. How does he want to add it? I'm not able to understand. See, we are not, I'm not able to get it very clearly. Means, how does he want to add it? Means, the thing is, see, moment the saturated temperature and pressure are fixed, the state is fixed. Right? Do you want to say that why don't we put up F equals to 2 there? The thing is, the state of the system gets fixed when either of the intensive properties get fixed. So that is the only thing that is told by Gibbs phase rule. Gibbs phase rule just tells you that moment you fix up one particular property, the state gets fixed. When it is a liquid vapor mixture and he fixes the composition, automatically at that particular composition of liquid vapor mixture, he cannot change the temperature and pressure. And that is what Gibbs phase rule tells. Gibbs phase rule simply states what are the minimum number of intensive properties that you require to fix the state of the system. If in a liquid vapor mixture you specify the quality as say zero point 0.6, and to fix up the pressure is fixed, then in that case the temperature automatically gets fixed. Gibbs phase rule does not tell you anything about the composition. I think was this his first question? I don't remember. Was this his first question, that whether we should include composition or something? Some question he had asked me in the beginning. I don't remember what was the Bonusri. He had asked something of this sort. What I
Yes, ma'am.
want to, what I
How
want to,
many,
uh,
sorry, how many independent intensive properties are required to fix the state of pure substance? Is
yeah,
it one or two?
no, that I had already answered. I think he has understood. So therefore, it depends upon how many phases are in equilibrium. Depending upon the number of phases which are in equilibrium, the number of independent intensive variables have to be specified. When two phases are in equilibrium, one particular independent intensive property has to be verified. Moment that is verified, the two phase system gets fixed, but the composition within the two phase system does not get fixed. Just the two phase domain gets fixed. Within this domain, the composition can be varied. There is a specific reason why the composition can be varied, because with the composition, the mixture properties can vary. Right. So therefore, moment the temperature and pressure they are fixed, then within this particular domain, the quality can be changed. And as the quality is changed, the intensive and the extensive properties they can change. So therefore we are just fixing the state of the system as two phase, whether the state of the fixing system is single phase or whether the state of the fixed system is two phase. That state of the system we are fixing. But remember one thing, there is one particular anomaly here, that within the two phase system we are not specifying the point exactly where the system lies. That is the drawback of the phase rule. I think this is where his confusion is. That is
He's
what.
again
Huh, tell me.
asking that can you
Hmm.
please explain without constant enthalpy process to find dryness fraction? You maybe explain it different way.
Once more.
Can you please explain without constant enthalpy process to find dryness fraction?
I see. See, why I used the constant enthalpy thing, I used it just because this is the standard way to find out dryness fraction in industries. That is why I had used it. What I wanted to tell you is that suppose, see, you are drawing a T versus V, right? This is the two phase line. Fine. So therefore, the constant pressure lines, if we draw, this is the line. Fine. So therefore, within the two phase dome, either the temperature or the pressure can be specified. But within this two phase dome, by specifying either the temperature or the pressure, if the state of the system, we know that this is going to lie within this dome, but we do not know where exactly it is going to lie. It can lie anywhere. Therefore we need another additional parameter to specify the state of the system, and that particular parameter, that can either be the molar volume, or it can be the molar enthalpy, or it can be any molar property, or it can be the dryness fraction. So therefore there are different ways by which the dryness fraction can be estimated. It can be estimated from any mixture molar property. I had taken the specific, see, suppose it is T versus V. So therefore, if it is here, the dryness fraction is something, and accordingly, the molar volume is something, right? So therefore, depending upon where it is there, depending upon its position, the molar property and the dryness fraction, it is going to change. If you fix up one, what I meant to tell you is that within this particular domain, if you know the dryness fraction, all other mixture properties can be specified. Or in other words, if you know one particular mixture property, then all other mixture properties and composition are specified. But yes, you are correct. Within this particular dome, simply the state of the system is defined. The state of the system, it is two phase, it is not single phase. Just that particular state of the system is defined, but we do not specify, or we cannot identify the composition of the system within this particular domain. I think there only maybe the miscommunication was happening. I accept, or I repeat once more, that just by specifying or from Gibbs phase rule, we can simply find out whether the state of the system can be specified. What do I mean? Whether this system is in single phase or whether this system is in double phase. But it does not specify what is the composition, or rather it does not specify what is the proportion of the two phases. That is not specified. It just tells you it is two phase, no matter whether it is two phase with 10% vapor or whether it is two phase with 90% vapor. That it does not specify. It just tells you that this is in that under this particular condition, it is two phases in equilibrium, and for this uh, state, and for this state, it is simply in a single state situation. When it is in a single state situation, then we can vary the two properties. When it is here, we cannot vary the temperature and pressure, but we can play with the composition. No matter how much we play with the composition, the system still remains two phase. That is what I had meant to tell you, that within the two phase dome, no matter how much we are playing with the composition, the system still remains two phase. But if you want to find out the composition within the two phase mixture, then in that case, the standard technique is by using, Acha, well, I'll show you. Give me 2 minutes time. I'll just go to my Bonusri. Can you just tell me the HX plot? If I go to the HX plot, I think it will be easier for him to find, to understand. Give me 1 minute. I think I have the HX plot here. Hmm. hmm, Wait. Well, here if you see, no, this is not the HX. Acha, here also we can do it. Yeah. So therefore, this is the two-phase domain. Right. Now, in this particular two-phase domain, these are the constant quality lines. I'll just specify it and I'll just tell you. Well, if you see, this is the two-phase domain. I think this might help you a little. Why? In this, these are the constant quality lines which are there. Fine. Now, in this particular case, what we can do, these are the constant pressure lines which are there. These are the constant temperature lines. Now, what we can do, suppose we are at this particular point. We know what is the H, we know what is the S, and this is in a two phase dome. Now we do not know what is the quality. So what we can do, we can follow one particular.
Ma'am,
Yes,
the live session has been ended, so nobody is able to see your
এই মরেছে.
videos.
So
No, no,
therefore,
madam.
huh,
Madam, go ahead, go ahead.
Okay.
no,
Carry on,
one thing
madam.
I can tell you, this is one student who is asking questions. If I could have interacted with him by miss, if he could have talked to me, it would have been better. So for that one student, I can just tell him that you just send his my email to him, right, and ask him to contact me. So I'll
Okay, ma'am.
sit with him separately and I'll explain the whole thing to him.
Okay, okay.
Okay, ma'am.
That will be good because it's just one student. So for that, all of us need not get set up. Just ask him to send an email to me and to ask for a time. I'll sit with him and I'll explain this dryness fraction to him. Can you tell me his background, please? Is he from industry?
I don't know.
No, you cannot tell. I think NPTEL, if there's somebody, they can tell. Is there anybody in from the NPTEL office?
Yes, ma'am.
Acha, can you just tell me the background of this particular? Is he from industry or is he from some particular academic?
Actually, sir, ma'am, all students are in chat box. Okay,
Oh, ho,
so
ho, ho,
we
ho.
can't verbally or physically not contact now.
Oh, you do one thing. Either Shumon or Bonusi, you just post him and you give him my email
Yeah,
address.
madam.
Okay, and to
Okay.
tell him to contact me. Then in that case, maybe I'll arrange a my Teams meeting or a Zoom, or I'll ask you NPTEL people only to do it just for me and him. I think that is possible, isn't it?
Yes.
So then I'll sit with him and I'll explain that to him. Bonusri,
Yes.
you
Yes,
do
ma'am.
one thing. You tell him that let him jot down all his doubts, okay, and send them to me. Fine.
Ma'am, he is
Dryness
sending
fraction.
that he's
Huh.
a graduated student.
Perfect. Perfect. You tell him that he can jot down other doubts regarding dryness fraction. I can talk to him. Okay, if he has got other doubts, then let him specify or let him write down all the doubts. Okay, then one more day I'll request the NPTEL people. That day you also may not be there. If it is possible that both of us can talk and interact, that will be the best thing.
Madam, you
So
can
therefore
also
in
book
half
the
an hour,
another sessions from NPTL.
no, we can book another, but what I want is I want to talk to him. That will be easier instead of this writing down the questions.
So, madam, you want to in future you want to one-way VC, one-to-one VC options. You can.
Nay, that see next, if I get such an enthusiastic student, I would want. Okay, so
Okay.
but for this particular case, it will be good if a one-to-one session can be arranged where I can sit with him and I can sort out his doubts.
Okay, madam, no problem. You can share the student details, then it will be
Possible.
possible.
What do I need to do? Share the student
Share
details.
the student details. Actually,
I think
madam.
Bonusri has that. Bonusri, you have the student details, isn't it?
I have got his mail ID.
Very
Okay,
good.
then madam, we can arrange the
Yeah.
one to one or one
Just one to
to.
one you arrange in Zoom or something, both of us will be talking. I think that is going to be easier.
Okay, madam.
Okay, so
Okay,
one I think 15 to 20 minute session if you arrange, then I can see because since he has got questions, I can sit with him and I can sort out his doubts.
okay, madam. And what, which date you want to take the video
Tomorrow,
conferencing?
tomorrow or day after, I can take it.
Okay,
No
so
point in.
madam, first you will confirm with the
Yeah,
student,
yeah,
then you will confirm me.
yeah. That will
Okay,
be good.
okay,
Okay,
madam.
and then I
Okay.
can sort out even. In fact, Bonusri, you can also post that, or Shumon can also do it. That well, we can have another interaction session, and if they are interested, then maybe we can have it on Monday or anytime. Saturday also we can have it.
Okay.
Saturday morning also we can have it. Not a big deal. Okay, Bonusri.
Okay, ma'am.
Yeah, Saturday morning also around say for to say 11.
No
Okay,
problem.
so therefore
Okay.
but what you tell him is dryness fraction. Madam will try her best to make you explain. If you have any other doubts, then please share those doubts also. Okay,
Okay.
and if many people are not interested, one or two, then we can have a Zoom meet where he can talk, I can talk, and I can explain things to him. I think that's going to be easier.
Okay, ma'am.
So I think Shumon, I think so we are done for today.
Okay, ma'am.
Okay, so on Saturday
Madam,
at 11. Yeah,
one thing that first you will confirm from student
yeah,
side.
yeah.
Okay, then you will
Okay.
decide the which date you want to.
Yeah, see, Saturday 11 a.m. is fine for me. That I'm telling you. So you can
Okay.
always propose to him that Saturday 11 a.m. madam was suggesting.
Okay, okay, ma'am.
That will be good. Okay.
Okay,
So
okay.
that will be fine. Okay. Acha, one thing I would like to ask both Shumon and Bonusri, since I was writing in this particular way, was it difficult that I did not make the screen, the screen for the full screen?
No, 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 madam. This is the that is visible and good.
Yes,
Because see, if
quality
I
is
wanted, yeah, if I wanted to, means otherwise I could have shifted, but I find this thing to be easier. So that's
Okay,
why I
no
asked.
problem, madam. That
Okay,
is good.
okay, okay, fine,
And
fine.
Bonusri,
Thank you.
please contact this student and you can confirm me.
sure, sir.
Okay.
Saturday 11 Bonusri.
Yes, ma'am.
Okay. So I
Okay.
think then we are done today. Thank you very much.
Okay. Thank you, ma'am.
সুমন, thanks a lot.
Thank you.
বনশ্রী, thank you. এই কি
Thank you.
হলো রে অ্যালেক্সের? বুঝতে পারছি না তো।